All right, today's lesson is on logistic growth, and so we're going to talk about some very important facts about the logistic growth function that you need to know, and this is one of our differential equations that we take a look at. And so in exponential growth or decay, we assume that the rate of increase or decrease of a population at any time t is directly proportional to the population, so that dp dt is equal to kp. And this is what the graph right here of an exponential growth looks like. It continues growing with no stopping point. And so the difference between exponential growth and logistic growth is that in logistic growth, in many situations, the population growth levels off and it's approaching what we would call a limiting number or a carrying capacity because of limited resources. And so here's what the graph of a logistic growth function might look like. And it is modeled by this differential equation. dp over dt is equal to k, which is some constant, multiplied by p, multiplied by L minus P, where L is your carrying capacity, or that limiting number that we talked about. Now, you might see this equation in a couple of different forms. They don't necessarily always use P. Sometimes they like to use Y instead. So you might see this as dy dt is equal to ky multiplied by L minus Y, where Y is taking the place of P. Or you might see it in a completely different form altogether, such as this, ky multiplied by 1 minus y over L. You need to be able to recognize both forms because both of them show up on the AP test, and you need to be able to identify out of each form where the limiting number occurs. And so depending on what that equation looks like will determine where your limiting number, or from now on I'm going to call it the carrying capacity, will show up. Okay, if we find the second derivative of p with respect to t, or y with respect to t, we can find out some important facts about the time when the population is growing the fastest, and we're going to do those in the following examples of the notes. So I'm going to give you a chance to pause the video here and read over the three examples that I give you of logistic growth, and I want to see if you can figure out sort of what the common elements of each of the three examples are. And go ahead and also read the back of the first page also, where I talk about Walmart and some of the things that Sam Walton did in his time as the CEO of Walmart in helping that business grow by looking at the rates of increase in the sales of particular items. So go ahead and pause the video and give yourself a chance to read that, and then go ahead and hit play whenever you're ready. Okay, so I'm going to give you one more example just before I start example 1 here. And the last example would be like that of Starbucks. Starbucks follows a logistic growth model because if you think about it, when Starbucks first got started, the number of stores of Starbucks coffee, it started to grow slowly. They started with one store, it got real popular, so they had to add a second. And then that got real popular, so they had to add a third. And all of a sudden, the number of Starbucks stores started to explode and grow really rapidly, until finally what they realized is, okay, we're opening too many stores. We've got to slow down the rate at which we are opening stores. And so that rate started to decrease. And that's where that point of inflection occurs. And so you start to see the increase of the number of Starbucks stores start to level off and reach a carrying capacity. Okay, so with that being said, let's take a look at example 1. It says the population P of T of fish in a lake satisfies the logistic differential equation dP dt is equal to 3p minus p squared over 6,000, where t is measured in years, and we have an initial condition or an initial population of 4,000. And we're going to come back to that here in just a minute. Now, this equation is not really in a form that is helpful, and so what I'm going to do is I'm going to factor it into a form that is helpful by factoring out the leading term. So if I factor out a 3p, that's going to leave me with a 1, since if I divide this term by 3p, it gives me 1. And then minus, when I divide this term by 3p, it's going to leave me with a p, and then 6,000 times 1 over 3, it ends up being 18,000 in the denominator. And so now, the way that this is set up, I see that my limiting number, or my carrying capacity, L, is equal to 18,000. And so what that represents is it represents the limit as t goes to infinity of p of t. And so now I am able to answer the first question here, part A, which is 18,000. Okay, and what I want you to notice is that our initial population of 4,000 is smaller than my carrying capacity. So P of 0, my initial population, is smaller than L. And so what that means is that this population of fish is going to grow logistically from an initial population of 4,000 until it reaches the carrying capacity of 18,000. And so the range of the solution curve is going to start at 4,000, and it's going to go all the way up until 18,000. And I've got, oops, sorry about that. I've got an equal bar here on the 4,000 because the population will actually equal 4,000 initially, and I do not have an equal bar on the 18,000 because we'll never actually reach 18,000 since it serves as a horizontal asymptote to the graph of the logistic curve. Okay, for part C, for what values of P is the solution curve increasing or decreasing? Justify your answer. And so to do this, we're going to run a first derivative test by saying dp dt is equal to 0. And so that's going to happen at P is equal to 0. So that's taking into account this first factor, 3P is equal to 0. And it's also going to occur when 1 minus P over 18,000 is equal to 0. And so if I solve for P there, I'm going to get that P is equal to 18,000. And so now, if I run my number line, I've got 0 here, and I've got, and really I don't even have 0 because remember, my population is 4,000. So really I've got 4,000, and I can't go any further to the left here. So I've kind of got to X that out and put 4,000 there, and then I've got 18,000 here. And if I choose a number that's in between those, let's say 10,000, then if I plug 10,000 into my first derivative, 3 times 10,000 is positive, and then 1 minus 10,000 divided by 18,000, 10 over 18 is less than 1. So 1 minus a number that's less than 1 will also be positive, and so this will be positive, and I'm not going to check anything above my carrying capacity because I know the population will now never go over my carrying capacity. And so P is increasing, so the population is increasing here on the entire range. So it's increasing on 4,000 until 18,000. Okay, in letter D, we want to know for what values of P is the solution curve concave up or concave down, and justify your answer. So here I'm going to take the second derivative of P with respect to t. And so if I go back up to this original equation, the way it was written on the paper, the derivative of 3p will be 3 times dp dt, since I'm taking the derivative with respect to time, and then minus 1 over 3,000 times p times dp over dt. Now what I'm going to do is I'm going to factor out dp over dt to make it a little easier, and that's going to leave me with 3 minus p over 3,000. Okay, so if I set this equal to 0, I get that dp dt is equal to 0, or I get that 3 minus p over 3,000 is equal to 0, and if you solve that for p, you're going to get p is equal to 9,000. And we're going to see that's a very significant number in this problem, and you may have already noticed, oh, 9,000, well, that's half of the carrying capacity. And if you realize that, you've got good instincts, because that's where our point of inflection is going to occur on this logistic growth graph, which is half of the carrying capacity. So if we do a little sign chart here, d squared p over dt squared, and what does that tell us about p? Well, we're going to have 4,000 on here, we're going to have 9,000 on here, and we're going to have 18,000 on here. And so if I plug in a number that's between 4,000 and 9,000, let's say 5,000, just for, you could choose whatever you want to between 4 and 9,000, but if I try 5,000, then dp dt from our previous exploration, that's going to be positive. And then 3 minus 5,000 over 3,000 is going to be positive. And so this is going to be concave up in this interval from 4,000 to 9,000. If I plug in something that's bigger than 9,000, let's say 10,000, then in that case, dp dt is going to be positive, again, because of what we discovered up here. And then 3 minus 10,000 over 3,000 is going to be a negative value. And so this is going to be negative and concave down. And so what we see is that P is concave up as long as the population is less than half of the carrying capacity, and P is concave, sorry for the bad handwriting here, concave down as long as the P is bigger than the carrying capacity. So I'm going to say 9,000 is less than P is less than 18,000. So if that P is bigger than half of the carrying capacity, so notice this 9,000 is 1/2 of L. This is equal to 1/2 of L. This is equal to 1/2 of L. That's where we have our point of inflection. So letter E, does the solution curve have a point of inflection? The answer here will be yes, at P is equal to 1/2 of L, which in this case, for this particular problem, is equal to 9,000. And the justification is since P changes from concave up to concave down at P is equal to 9,000, which again is equal to 1/2 L. And what I want to tell you right now is that when you are working logistic growth problems, listen to me very carefully, please just memorize this fact. Not necessarily that it happens at 9,000, but more specifically that the point of inflection occurs at half of the carrying capacity, and more specifically that the graph of the logistic growth function changes from concave up to concave down at that point of inflection. It always happens that way. Okay, so dp dt changes from increasing to decreasing. The rate of change in the population always changes from increasing to decreasing at the point of inflection, which occurs halfway towards the carrying capacity. So use the information you found to sketch the graph of P of T. So the first thing that we know is that we have an initial population at 4,000. We have a carrying capacity at 18,000, so we'll draw a little horizontal asymptote there, and then halfway towards that carrying capacity, we're going to have a point of inflection. And the graph will always be increasing, but it will start off concave up, and then once it gets to that population of 9,000, halfway to the carrying capacity, we will change to be concave down. Now, question at the bottom of the page. What if the initial amount was different? What if P of 0 was 10,000 or 20,000? Which of your answers would change? And the homework that you're going to work will give you an opportunity to explore that more thoroughly, but we're going to look at just 3 of the questions on the next page. Okay, so notice we've got the same exact differential equation here, except this time the initial population is 20,000, which is bigger than our carrying capacity, which was L. And remember from the previous example that L was equal to 18,000. And so now what this is going to look like is that we have this carrying capacity at 18,000, but now our initial population is 20,000, and this pond that these fish are living in, it cannot sustain 20,000 fish. It can only sustain 18,000 fish, the carrying capacity. So what's going to happen is that our graph is going to quickly decline back to that carrying capacity, and it's going to be concave up in doing so. And so we're going to see that as we work this example. So for what values of P is the solution curve increasing, decreasing? Okay, so I'm going to take dp dt is equal to 0, and we saw earlier that that happens when P is equal to 0 and 18,000. And so here I've got 18,000. Here I've got my initial population of 20,000. And so if I plug in something like 19,000 into dp over dt, and I'm going to use my factor version that we had on the other page, dp and then 1 minus p over 18,000. So now if I plug 19,000 in for this p, 19 over 18 is bigger than 1, and 1 minus something bigger than 1 is going to be negative. And so this is dp dt. What that's telling me about p is that p is going to be decreasing, and so we can say that p is decreasing from 18,000 less than or equal to p less than or equal to 20,000. So that bears out with what we saw on the graph, is that graph is going to quickly decrease back to that carrying capacity. And then for what values of p is the solution curve concave up or concave down? And for that I have to look at my second derivative, and we'll see if I can remember what that was from the previous page. I believe it was dp over dt and then multiplied by 3 minus p over 3,000. Okay, and so that was equal to 0 at p is equal to 0, 18,000, and 9,000. But 9,000 isn't applicable to this graph because the graph's range is from 18,000 to 20,000. And we could even go ahead and even put that on the next part, is that this is going to be 18,000 is less than p is less than or equal to 20,000. And so 9,000 doesn't even come into play here. So if I just put 18,000 and 20,000 and I plug in 19,000, then this right here is going to be negative, and this right here is also going to be negative, and so that will give me a positive, which means that p is going to be concave up. So p will always be concave up whenever the initial population is bigger than the carrying capacity. So on the entire range here, p is going to be concave up. Okay, so here are 5 important facts that you need to memorize and know very well about logistic growth differential equations. I don't want to necessarily read these word for word to you, but I do need you to know what these facts are and that the logistic growth model follows these 5 things. And you can memorize these for every logistic growth model. You don't have to work out all of the details like I did in the examples. That was really more for us to discover these 5 facts, okay? So you don't have to do that on every problem. It's just a matter of memorizing that the limit is t goes to infinity of p of t. That is equal to the carrying capacity, which is L. And so that was fact 2 that I just explained. Fact 4, a point of inflection occurs on the graph of p whenever p is equal to half of the carrying capacity, and at that point the graph of p will change from concave up to concave down. That will always happen. Okay, so please look over these, please memorize them, and know them very well. Okay, so we're going to finish off with 3 AP problems on logistic growth. The function n satisfies the logistic differential equation. dn over dt is equal to n over 10, 1 minus n over 850. So I notice a couple of things, that this is in the form dp dt is equal to p kp 1 minus p over L. I almost wrote 850, but what I meant to write was L there. And so what I see based on that is that this 850 represents the carrying capacity. So L is equal to 850. That tells me a lot of things about this logistic differential graph. And I also see that n of 0 is equal to 105. So that means that n of 0 is less than my carrying capacity of 850. So I know I'm going to have a point of inflection at n is equal to half of the carrying capacity, which will be 425. That's where my point of inflection will occur. I know that that the graph of n will change from concave up to concave down at that point. There are a lot of things I know based on the previous facts that we discussed on the previous page. Okay, so which of the following statements is false? Letter A says the limit as t goes to infinity of n of t is equal to 850. Well, the fact that my L is equal to 850 tells me that this statement is true. That limit as t goes to infinity of n of t is going to equal 850. Letter B, dn dt has a maximum value when n is equal to 105. Well, I know that dn dt is going to have a maximum value at the point of inflection. So really, this is going to happen not at n is equal to 105, but at n is equal to 425, where that point of inflection occurs. And so this number right here makes this statement false. And so I know that that's my answer. I'm going to go ahead and look through the rest of them and see if these are accurate. So letter C, the second derivative equals 0 when n is equal to 425. I know that's where my point of inflection is going to occur. And so it would make sense that my second derivative is equal to 0 there. And so I know that that's a true statement. I'm also going to mark out A since I knew that was true. And then letter D, when n is bigger than 425. So that's on the other side of that point of inflection, because I know the point of inflection is at n is equal to 425. And so on that other side, I know that n is still going to be increasing, except now it's going to be concave down. And let's see if this lines up with that thought. dn over dt is greater than 0 means that n is increasing, and d squared n over dt squared less than 0 means that n is concave down. And so that checks out with both of the things that I know about the logistic growth model. Okay, next one. It says a population y changes at a rate modeled by the differential equation dy dt is equal to 0.2y times 1,000 minus y. Now, a lot of the times the question will tell you that it's a logistic differential equation. Here, they do not say that, so you have to be able to recognize that this differential equation is the logistic growth model. And so I see that right now it is in the form dy over dt is equal to ky times L minus y. And so that means that this 1,000 is going to be my carrying capacity, or my L. And so now it says, what are all values of y for which the population is increasing at a decreasing rate? And so if we translate that, increasing at a decreasing rate means that dy dt is going to be positive. And if it's increasing at a decreasing rate, that means that the second derivative is going to be negative, because if the second derivative is negative, that means the first derivative, the rate, is decreasing. I hope that's making sense for you guys. Okay, so when is dy dt going to be greater than 0 and the second derivative of y going to be less than 0? That is going to happen after the point of inflection. And so when is the point of inflection going to occur? That's going to occur at half of the carrying capacity, which will be half of 1,000, which of course will be 500. And so this is going to occur whenever y is greater than 500. Okay, and then the final question says the number of students in a cafeteria is modeled by the function p that satisfies the logistic differential equation 1 over 2,000 p times 200 minus p. So automatically you should be able to recognize a couple of things from this differential equation. The first is that 200 represents your carrying capacity. T is the time in seconds, and p of 0 is equal to 25. So I see that p of 0 is less than 25, which means it is, it's equal to 25, which is less than my carrying capacity of 200. And so that means I am going to have a point of inflection at 1/2 of L, which will be 100. The question is asking, what is the greatest rate of change of students per second of the number of students in the cafeteria? Now, here's where it gets tricky. If we want the greatest rate of change, that means we want dp dt at the moment when there will be the greatest rate of change. And so that's going to happen at p is equal to 100. The common mistake here is that people just answer 100. That's where the greatest rate of change occurs. But the greatest rate of change, I have to plug 100 back in to my differential equation. So dp dt evaluated in p is equal to 100 is going to be 1 over 2,000 multiplied by 100 multiplied by 200 minus 100. And so doing a little bit of arithmetic here, this will be 1 over 2,000 multiplied by 100 times 100. And so that will be 1 with 4 zeros divided by 200. And so this will end up being 50 as my answer, I believe. Okay, so that'll do it for logistic growth. Please let me know if you guys have any questions.